As the last part of this activity, I'd like to show you how we can do an easy calculation to predict to what degree a chemical reaction will occur between a corresponding acid and a base. Now, in this case, we're looking at reactions of acids not with water or bases with water, but rather species that, in a sense, don't involve water. And so in this first case, you can see that it's a reaction with this alcohol and hydroxide. And I want to know, to what degree is this reaction going to go? Now, at first, we might want to back up a bit and remember that the lower the pKa, the stronger the acid. And in a sense, these kinds of reactions, you're comparing two different acids. So you've got the alcohol and you have the water, and in fact, we already said they're pretty similar. But as it turns out, the alcohol is slightly more acidic, at least in this case, than water, because it has a slightly lower pKa. But we'd like to put a more precise number on, well, to what degree would this reaction occur? Now, the approach is, well, one, you need to know the pKa's of the two acids in the reaction, the reactant acid and the product acid. And then we apply the following formula. So we go pK equilibrium is equal to the pKa of a reactant minus the pKa of our product. Now, I'll just remind you that the pK equilibrium is equal to the negative log of the K equilibrium. So anytime you have P, of course, it's just a negative log. So what we're going to do here is plug in, first of all, the pKa of the reactant minus the pKa of the product. And when you do this calculation, you end up with negative 0.2. At this stage, we have pK equilibrium is equal to negative 0.2. But just like pK equilibrium is equal to the negative log of K equilibrium, what we're going to do here is solve for the K equilibrium, which would be 10 to the negative pK equilibrium. So in a sense, that's like taking the anti-log, if you will. Okay, so this would be 10 to the negative 0.2. And so we end up with 10 to the 0.2. I ask you to calculate this further. Don't leave it as a fractional exponent. So 10 to the 0.2 is equal to 1.5. And so what this is telling us is that for every one reactant set of molecules and ions, we have 1.5 products. And so we have a slight excess of product at equilibrium. This reaction is product favored, but just barely. So in the next example, we're going to start with methanol, but let's consider, well, what if we want this reaction to really go in favor of the product and have a lot of product form at equilibrium? And so perhaps what we'd want to do is take a stronger base. So if you consult your table again in teaching model number 3 and think, okay, what's a stronger base than hydroxide? And hopefully you arrive, oh, a stronger base than hydroxide would be the amide. So let's take a look. So here's our methanol again. But instead of using hydroxide, let's use the amide anion. And then consider, well, what would be the products? Well, if my methanol acts as the acid, it donates a proton, the amide would pick up a proton. Well, of course, I would form the ammonia right here. Again, I would need the pKa's, and certainly in any assignment or even a test situation, you'll have access to the charts like teaching model number 3, so you will know the values. Now, usually there'll be substantially different pKa's. The pKa that I'm going to use for my methanol will be 15, and the pKa that I'm going to use for the ammonia is going to be 35. The pK equilibrium is equal to the pKa of the reactant minus the pKa of the product. We'll write in here the 15 minus the 35, which of course is equal now to negative 20. We will solve for the K equilibrium, which is equal to 10 to the negative 20, which is equal to 10 to the 20. And essentially this just means that the K equilibrium is equal to 1 times 10 to the 20. And so this is telling us for every one of our reactants, there's 10 to the 20 products. Clearly, this reaction is product favored. And so by using this much stronger base, we can be very effective at taking off the proton on the alcohol. So hopefully you can see that this kind of calculation is really quite useful in determining to what degree will a reaction go as written. So I ask you to consider the next reaction, and we'll go over it in a second. So that's the reaction of the carboxylic acid with the hydroxide. Okay, so now let's take a look at that reaction. Here is the outcome, but I do want to draw your attention to the fact that this is a reaction that you've seen a number of times. You've done titrations with this, for instance, in first year, where you titrated the acetic acid with hydroxide ion. And one of the things about titration reactions is essentially we rely on them going to completion. Well, this calculation, in a sense, guarantees that it does indeed go to completion. So the pKa for the typical acetic acid, around 5, pKa for water around 16. So pK equilibrium, 5 minus 16 equals negative 11. K equilibrium is therefore 10 to the negative 11, or 10 to the 11. So clearly this is product favored, and we've already seen that this reaction indeed goes to completion. So this is the introduction and review of acid-base chemistry. As mentioned before, when we get to chem activity 14, we're going to start to look at the theoretical basis for why organic compounds in particular have certain relative acidities.